Alright guys, today we are talking about domain and range symbolically. Okay, so for our first example, I would like to quickly look at the function f of x equals 1 over x minus 4. What is the closest function that we've looked at so far to this guy? Probably 1 over x, right? We've looked at 1 over x a bunch of times. The only difference here is that instead of the denominator just being x, we now have x minus 4. So this guy is gonna look like 1 over x, but what will be different about it? So let's think back to our last lesson on transformations. In transformations, we discussed that if we subtract 4 on the inside, what's going to happen? If we subtract 4 on the inside, well, inside was affecting the x values, right? We are subtracting 4 from x here. So subtracting from the x values, moving horizontally, always does kind of the opposite of what we think it's going to do. So if we were subtracting, we would think that the negative direction would be to the left, but it's actually going to go to the right. So it looks like 1 over x shifted right by 4. So let's go ahead and draw this. So before, I'm going to draw this in pencil, before our graph of 1 over x looked like this, right? It's very light, it's in pencil, you don't have to draw it. Now we're shifting to the left 4. So this asymptote, this vertical asymptote at x equals 0 is now going to occur at x equals 4. And we're going to have the same shape, just shifted to the right. Right, this is 4. So looking at this, what is the domain of this function? Well, the domain here starts at negative infinity. We continue along the graph to the right and end at 4, right? Remember, with an asymptote, we approach but do not touch it, especially for vertical asymptotes. Pick up again at 4 and continue all the way to positive infinity. All right, so what's going on here? Our domain is excluding 4. Can we see from this function that we have to exclude 4 from our domain? Well, what happens when I plug in 4 for x? If I plug in 4 for x, I've got 4 minus 4, which is 0, in the denominator. Is it okay for us to have 0 in the denominator? It's not, right? Because it's going to give us this asymptote. So let's make note of that. The function is undefined at x equals 4 because 4 minus 4 equals 0, and 0 in the denominator is undefined. So if we didn't have this graph and we were just looking at this function and we knew this information, what could we have done to figure out the domain? Well, we know we don't want our denominator to be 0, so we could just take the denominator and set it not equal to 0. How can we do this? Again, we take the denominator, set it not equal to 0. In this case, our denominator was x minus 4. And if we solve for x here, right, we add the 4 to both sides, we get x does not equal 4. Okay, let's use this method to solve a couple of problems. Let's look at the lab manual in the domain of a function lesson. This is number 1. So here, g of x is x minus 2 over x plus 5. What is the domain of this? So we just saw that if we have a denominator, all we need to do is look at whatever's in the denominator and figure out where it's 0. And that's what we need to exclude from our domain. So let's take our denominator, which is x plus 5, and say, I don't want this to be 0. Then we solve for x. Subtract 5 from both sides. We get x cannot be negative 5. Notice that our numerator doesn't affect our domain. As long as we have a simple polynomial or line or just regular old x's and constants on top, the numerator does not affect our domain at all. What is this in interval notation? Well, I know sometimes this can be a little bit difficult to figure out. Let's draw a number line just to help us keep track. Our only important value here is negative 5. That's the only piece of information we're looking to kind of document. And we know that because we don't want x to be negative 5, we're going to leave this as an open point. We want to shade in every x value on the number line that works for this function. So we're just excluding negative 5 and shading in everything else. Here we have two pieces. One piece that starts at negative infinity continues all the way to negative 5. We stop at negative 5. Then we have a second piece that starts at negative 5 but doesn't include it and then continues all the way to positive infinity. And this is our answer. All right, let's look at number 2. So this is h of x equals x plus 3 over x squared plus 2x minus 15. Like we said last time, we don't have anything funky going on in our numerator, so we just have to pay attention to what's going on in the denominator. All right, so we just need to check and see where our denominator equals 0. We want this to be not 0. How can I figure out where a quadratic is not equal to 0? What do we have to do? We have to factor. We have to factor. So factoring here, maybe you use the AC method, maybe you don't. Factoring here is going to give us x plus 5 and x minus 3. Right? Positive 5 times negative 3 equals negative 15, and positive 5 minus 3 equals 2. The reason why we factor is that what we can do now is we know we've got two things that we're multiplying together to get 0, potentially, right? This whole thing is going to be 0 when either this is 0 or this is 0. There's no other way for us to get 0. One of these has to be 0. we check and see where this is 0 and where this is 0. So we solve for x here. We get x cannot be -5. We solve for x here. We get x cannot be +3. Those are the two values we want on our number line. And similarly, we're going to have open points and then shade in everything else. So our domain here now has 3 pieces: -∞ to -5, -5 to 3, and 3 to infinity. Okay, last but not least, we've got k of x. Very similar to the last one. Why don't you guys give this a shot? Pause the video, see what you get, and then I'll give the answer in just a second. Okay, this is what I got. We have to factor this denominator. We set it equal to 0 after we set it equal to 0. I got x plus 4 and x minus 1, right? +4, -1 multiply to give us -4 and add to give us +3. We split it up, we get that x cannot be -4 and x cannot be 1. And then we stick it on the number line, we see that we're going to have 3 pieces, and we end up being from -∞ to -4, -4 to 1, and 1 to infinity. Sometimes I find that it's helpful to think about this, instead of thinking about it as 3 pieces, thinking about this piece kind of as a set of symbols that are saying, I'm taking -4 out of the domain. And thinking of these guys as a set of symbols saying, I'm taking 1 out of the domain, right? If that doesn't make sense or doesn't feel helpful, don't worry about it. But if it does, great. This is our answer. And yeah, let's continue forward. All right, so another function we've looked at before is this guy. F of x equals the square root of x. So the graph of this guy looks like this. Right, we start at the point 0, 0, and then it's got this sort of swimmer's arm shape is the way I like to describe it, continuing to infinity. What is the domain of this function? Well, nothing going on over here. We start at x equals 0 and we continue to positive infinity. We're including 0 because we have this point here, right? Square root of 0 is 0. So that is included in our domain. But our domain is just 0 and all positive numbers. Why is that? Well, we cannot plug negative numbers into even roots. So f of x is only defined for x values that are greater than or equal to 0. So why is this? Well, the square root function is always asking us, what number can I multiply by itself to give me this x value? So for instance, if I have the number 4, and I ask you what is the square root of 4, that's asking what number can I multiply by itself to give me 4? Well, the answer is 2. And also -2. Right? What number can I multiply by itself to give me -4? Is there anything? Well, no real numbers, because any positive number that I multiplied by itself is going to give me a positive number, and any negative number that I multiply by itself is also going to give me a negative number, because two negative numbers make a positive. So we will never have two of the same number that will multiply to give us a negative number. So there are no real number solutions when I take the square root of a negative. So because we're not defined for negative numbers, we are only defined for x is greater than or equal to 0. So for example, let's say we're looking at something like this. Let's say we have g of x is the square root of x plus 3. So what's up with this function? We know from transformations that what's going on with this graph? What's different about this graph from this one? It's shifted to the left or right? To the left. Right, we've shifted to the left by 3. We're adding on the inside, right? So we've shifted to the left by 3, and that is what our graph looks like. So what is our domain here? Well, it's just shifted to the left by 3, so -3 to infinity. Notice, I said we cannot plug negative numbers into even roots, right? And that is true. But for instance, what happens when I plug in -2 here? -2 is of course a negative number, but when I plug it in, I get -2 plus 3, which gives me the square root of 1, which does have a solution, right? Actually 2, positive and -1. So because of that, we are allowed to plug in negative numbers as long as once you compute everything underneath, what ends up being the number is not negative. So how can we look at this function on its own without looking at the graph and figure out the domain? Well, we want this to be not negative, meaning we want this to be greater than or equal to 0, right? We can take the stuff underneath the even root and set it greater than or equal to 0. So for instance, here, the stuff underneath the root is x plus 3. We want that to be greater than or equal to 0. We solve for x here. We subtract 3 from both sides, and we get x is greater than or equal to -3, which is what our domain is. Let's look at some examples of this. So this is again in your lab manual in the domain of a function lesson. So number 4, we have g of x equals the square root of 2x plus 8. Okay, so what do we want to do here? We said we want to take the stuff underneath the even root and set it greater than or equal to 0. So the stuff underneath the even root is 2x plus 8 is greater than or equal to 0. We solve for x. We subtract 8 from both sides. And then we divide by 2. So negative 8 divided by 2 gives me negative 4. We can draw this on a number line too if you would like. We've got negative 4. We want to be, this time we're greater than or equal to, so we have a filled in point. And we continue off to the right. In interval notation, this is bracket negative 4 to infinity. All right, number 5, we've got h of x is the fourth root of 9 minus 2x. This root is clearly even, so we do need to make sure that what's underneath is positive. So let's take that stuff. Positive or 0. 0 is fine. Greater than or equal to 0. We can again subtract the 9. We've got negative 2x is greater than or equal to negative 9. I divide by negative 2. When I divide by negative 2, what happens? This is kind of a easy to forget fact. When I divide an inequality or multiply an inequality by a negative number, I have to flip both the signs on the numbers, right? That's what we're doing when we divide or multiply by a negative, but I also have to flip the sign of the inequality. So I divide by negative 2 on the left, I flip the sign of the inequality, and then I divide by negative 2 on the right. So I have 9 over 2 or 4.5. On a number line, again, we have a closed point. This time we're looking at less than 4.5, so we shade to the left. And the domain of this function is negative infinity to 4.5, bracket. Last question here. K of x equals the cubed root of x cubed minus 8. Whoa, kind of scary, but not horrible, right? What do we need to remember here? This is a root function, but what type of root function is the one we have to worry about? An even root function, right? Even root function. So this is an odd root function, right? 3 is odd. Because this is an odd root function, we have no domain issues to worry about. Cubic functions look like this. Cube root functions look like this. And this guy has no domain issues. So we are totally fine. Domain of this is negative infinity to positive infinity. Oh, should square this guy too. Awesome. So let's kind of summarize so far. When looking for domain, if there is a denominator. Set it not equal to 0. And if there is an even root, set the stuff underneath the root greater than or equal to 0. All right, so those are all of our rules. When we get to looking at logarithmic functions, we'll have to look at some more domain rules, but for the most part, these are the only rules that are going to affect the domain of the functions we're looking at this semester. So, with that in mind, let's look at a couple of funky functions. So let's say we have the square root of x plus 3 over x minus 5. We've got our two rules. We know that because we have a denominator, we've got to set that denominator not equal to 0. And also, because we have a square root, we need to set what's underneath that square root, x plus 3, greater than or equal to 0. And solve. So here, we add 5 to both sides. X is not equal to 5. Here, we subtract 3 from both sides, so x is greater than or equal to -3. This is where the number line comes really in handy. We've got -3 and +5. We know we don't want to be equal to +5, so we'll draw an open point there. We know we're greater than or equal to -3 because we're equal to, we shade it in. We're looking for where we're greater than 3, so we shade in all the stuff greater than 3 except for 5. And then every x value that's shaded in here is all of the x values that satisfy this condition and this condition, right? So we write this in interval notation. We've got a bracket, -3, all the way to 5. We don't want to include 5. And then we've got 5 to infinity. This is our domain. Before we move on, I want to point out here that normally we don't have to care about what's going on in the numerator. But because the numerator has an even root, we have to worry about it, right? If we didn't have this square root here, the x plus 3 wouldn't be a problem. But because we have the even root, we have to make sure we account for that in our domain. Let's look at a couple more in the lab manual. This is number 10 in that same set of questions under domain of a function. So the first question here is f of x equals x plus 6 divided by square root of 8x minus 7. Let's say we're looking at this guy. So we know that what's in our denominator needs to not be 0. We also know that anything under a square root needs to be positive or 0, right? So if we want it to be positive or 0, but we can't be 0 because the square root of 0 will give us 0, which can't be in our denominator, then we know that the stuff that's underneath the root needs to be greater than 0, right? No longer greater than or equal to, strictly greater than. So when we solve for x here, we can we can add 7 to both sides. We get 8x is greater than 7, and then we divide by 8. 8 is positive, so we don't have to flip anything, and we get 7 is greater than 7/8. On a number line, we have 7/8. This time, 7/8 is open, but we shade everything to the right. And in interval notation, we have parentheses, 7/8 to infinity. A tip for WebAssign I'd like to mention, if you have a large text box that's asking you for a domain or really anything where it opens up the symbol pad, I think it's called CalcPad is what it's called, where it gives you the options for all the symbols. Don't ever round anything. Don't ever turn it into a decimal and round it. If you have a fraction, leave it as a fraction. That's my recommendation. That's just a quick tip. Okay, let's look at number 11. So with this one, we've got g of x is the square root of 8 minus x over x squared minus 5x plus 6. Okay, we're really getting our factoring practice in this lesson. So we have two things here. Again, we have both a denominator and a square root function. So we want to take each of them and deal with them individually. So our denominator here, when we have a denominator, what do? Well, we know that we can't divide anything by 0, so our denominator can't be 0, so we set it not equal to 0. What do we do on top? Well, we know when we're dealing with square roots, we can't take the square root of a negative number. It does not give us a real number solution. So we take what's underneath 8 minus x and set it greater than or equal to 0. So let's solve these both for x. Again, when solving a quadratic equation, we need to factor. We factor here, we get we want something that multiplies to positive 6 and adds to negative 5. Sounds a lot like negative 2 and negative 3. We split them up because we know that it's only going to be 0 when either of these factors is 0. And we get x is not 2 and x is not 3. We come over here to solve this guy. We subtract 8 from both sides. And then we divide or multiply by negative 1. When we divide or multiply by a negative, what happens to the inequality sign? We have to flip it. So we get x is less than or equal to positive 8. We draw this on a number line. Our important numbers are 8, 3, and 2. We look at 2. We don't want to be equal to 2, so we are going to leave that open. We don't want to be equal to 3, so we are going to leave that open as well. And we want to be less than or equal to 8, so because we want to be or equal to 8, we can shade it in. And then we want to shade everything less than 8. So shading to the left, not including 3, not including 2, and continuing to negative infinity. We get negative infinity to 2, 2 to 3, and then 3 to 8. Okay, let's talk about range really quickly. So when looking at range symbolically, it's very complicated to do sort of mathematically looking at the equation. So we want to utilize our transformation and graphing concepts. You're not going to run into something really wild or out there. You're going to be asked about problems where you just simply have to kind of look at the transformations that are going on with a basic function. So, for example, let's say you were given f of x equals the square root of x minus 3 plus 2. So all we need to do is think about what's going on with the graph here. What is our basic function that's related to this guy? X squared, right? What is the domain and the range for x squared? Well, our domain, we just talked about it. Our domain is 0 to infinity, right? Everything greater than or equal to 0. If we think about our graph, right, remember our graph was this guy. What's the range of this? Well, starts at 0, continues to infinity, right? So our range is also 0 to infinity. What's happening to our x and y values here? How are we changing them when we do the transformations with this graph? Our x's are shifting where? To the right by 3. What's happening to our y values? Remember, our x values are on the inside, right? And those affect us horizontally. Our y values are affected by things on the outside and move vertically. So things on the outside are going to affect us. The only thing on the outside here is plus 2. So our y values are shifted. Plus 2 shifts us up by 2. So our domain has been shifted to the right by 3, and our range has been shifted up by 2. Our new domain, and again, we could calculate the domain here, right? All we would need to do is set that stuff inside greater than or equal to 0. We solve, we get 3. Domain here has been shifted right by 3. We get 3 to infinity, right? And that's the same thing we got up here. Our range has been shifted up by 2. We used to start at 0. If we get shifted up by 2, it means we start at 2, right? Notice that our domain changes did not affect our range, and our range changes did not affect our domain. What happens if we multiply? Let's do minus 1 this time. Okay, so looking at this next one, let's just focus on range for the sake of time. So we're just looking at the outside of the function. Right, so what are we doing? We always want to follow PEMDAS. We're multiplying by 3, so we are stretching the y values by 3 and shifting them down by 1. Stretching them by 3, is that going to change our range? If I stretch that graph, that swimmer's arm, by 3, what's going to happen? Well, 0 times 3 is still 0, right? So the point 0 is not going to change, right? Multiplying, stretching in the positive direction does not shift our range. So this doesn't do anything. It doesn't make it more infinity, right? All the numbers above 0 are stretched higher, but that doesn't change the fact that we're still going to infinity. It doesn't make it extra infinity, any more infinity than before, right? It's still infinity. So this 3 actually doesn't really do anything. But what does do something is this shifting it down 1. Shifting it down 1 is going to change our range. How? Remember, before it was 0 to infinity. Now, shifting it down 1, it starts at -1 and still continues to infinity. Last example. H of x equals negative square root of x plus 5 plus 2. Okay, so what's happening to our y values? On the outside, this time we're flipping, right? Flipping our y values, flipping that function over the x-axis, does what to our range? If before we were looking at all of the y values greater than 0, and then we flip the sign of them, now we're looking at all of the y values less than 0, right? If I take this function and I flip it, right, that's all of these guys. So we now have the range of 0 to negative infinity. So y values are flipped. And then what happens? So we kind of have this intermediate, right, because we're not done, new range of negative infinity to 0, right? And then we shift up by 2. So if I'm taking negative infinity to 0 and I'm shifting it up by 2, what's going on? Well, we ended at 0 before. We're moving 0 up to 2. So our domain is negative infinity to 2. And that's all that's happening on the outside, so this is our final range. Okay, that's all I have for y'all today. As always, thank y'all so much for watching.